a rugged coastline facing the stormy Atlantic. We're off to southwest England, the Land's End Peninsula. Picturesque coves and, away from summer months, wild beaches, the magnet for surfers. The cliffs have attracted rock climbers for over a century. But as well as tourism and adventure, Cornwall has a post-industrial landscape, a product of mining and mineral processing. This has been one of the world's great metal provinces, extensively worked, but maybe not worked out. A future may lie in its critical metals and geothermal energy resources that could help to bridge the energy transition. I came to Cornwall nearly 50 years ago to rock climb, but now I'm back to look at the geology and its history and perhaps its future. England's southwest peninsula is studded by large outcrops of granite, here in red, along with other igneous rocks. We're looking at the far west, that's Land's End. There are different granite types, or facies here, along with country rocks. So let's go and visit some outcrops. Well, I've come down here to the far west of Cornwall. We're really close to Land's End. I've not gone to Land's End, you have to pay a large amount of money to go to the parking. So let's go here. We're in a place called Sennen Cove. And we can see it's a world of granite. So let's explore the origins of this granite, its tectonics, and see how the granite has impacted on the rest of the geology around here. It's a story not just of granite, but also a really important mineralisation and an industrial history. Okay, let's get going and explore this granite first of all. These outcrops are typical of much of the Land's End granite. It's a biotite granite with these big crystals of felspar several centimetres long. Traditionally, coarse-grained granites like this are interpreted to have cooled very slowly, but let's look more carefully. The crystals have also grown in xenoliths, so this is a subsolidus texture. The megacrysts are more like porphyroblasts in metamorphic rocks, and they don't reflect cooling rates. It's about crystal growth rates, and these can be very fast. So actually you can see quite a lot in this granite. We've got the megacrysts of felspar, but they're these xenoliths of presumably country rock. And actually the granite itself is differentiated, cut by this later vein, and this loose block that's fallen away shows it really nicely. Come and have a look at this. So the background megacrystic granite, and there's this later phase in here which is much lighter, finer grained, and there's a rim to it. If I look really closely in here, I can see this black speckledy texture, and these are, well, mostly tourmalines. Tourmaline is common in many granite complexes. They're sort of dustbin minerals, silicates that, along with boron, incorporate all sorts of residual cations left over during fractional crystallization. So tourmalines are often found in veins coating fractures that cut granites. Well, so much for the granite here. let's get away and see what the rest of the geology's got to offer in this Land's End Peninsula. Let's hope the weather improves. So the Land's End granite has been emplaced into country rocks. So this is the country rock to the granite, and you've got these really nice deformed rocks. Well, the miners around here referred to these country rocks as kilas, an assembly of metasediments and metavolcanic rocks that hosts the surrounding granite. But let's get away from the edge of the granite to see what these country rocks look like. It's another grade A in Cornwall. So to see the country rock that the granites around here were intruded into, I've come down here to Port Leven, and we've got these metasediments. Still see these siltstones, fine sandstones, thinly bedded, quite deformed and invaded by these veins. Quartz veins are common, part of the release of silicate-rich water during low-grade metamorphism, well before the granites were intruded. And it's not just metasediments. So these greenstone layers, they're basalts. Hard to see really in here whether they are intrusive and sills or whether they are eruptive. I think on balance they're probably sills intruded into this package of sediments and then all those deformed together. They're Devonian in age, once part of a continental margin deposited in what has been called the Gramscatho Basin. But all these rocks have been deformed and metamorphosed during the Variscan orogeny. And it's these strata that form the kilas, the country rocks to the Land's End granite. And they make for a pretty dramatic coastline. So these are greenstones. They're, well, metabasalts, low-grade metabasalts, part of the Gramscatho Basin. We'll look at the tectonics of the old basins and the Variscan orogeny later in this video. For now, let's go and look at how these country rocks relate to the granite and how the granite itself may be structured. Because large bodies of plutonic rocks like this are commonly thought of as frozen magma chambers. A big volume of melt, all slopping around, may be convecting and then freezing together. Well, for these granites at least, the picture is much more interesting. Well, I've come down here to find the contact between granite and the country rocks, the kilas. I think we route around on the far side of the cove. I think we'll really see what's going on. Well, the back of the cove here, we've got granite, and it's granite inland. In the distance there, forming that craggy ridge, well, those are the country rocks, the kilas. Well, let's go over there, see if we can find the contact. The granite is pale. The kilas metasediments are the dark rocks on the top of the cliff. So this is a roof
to the granite. Let's take a closer look on slightly easier ground, keeping well clear of the waves. The granite here isn't megacrystic, it's fairly normal looking, but it has a horizontal banding of a few centimetres across, and the upper bands are pegmatitic. So these are individual intrusions. They're sills of distinct batches of granitic melt. The contacts are diffuse, so these pegmatitic sills intruded into a crystal mush of the surrounding granite.
So that's quite a variety of fascies in the granitic composition as you approach the edge of the magma chamber. Its roof, from those rather finer grained layers to the more pegmatitic zones. So a lot of differentiation at the roof of the magma chamber.
So this really isn't a chamber full of melt. That's actually a really bad name for this kind of structure. The granite body is formed of stacked sheety intrusions, and we can see much more along the cliff line here. Let's explore these relationships on some of my field sketches with annotations and some more detailed parts which will capture some of the geometry. So the floor of this body has xenoliths of metasediment, but these align with the country rock fabric, and so do these towards the top of the big intrusion. So the xenoliths are not really sinking through the granite melt. The country rock is isolated by intruding wings of granite, and these wings are anastomos. The xenoliths, well, they're more or less in place still. And what about the magma batches themselves? Well, this shows the game. Pegmatitic blobs floating, well, sagging into the surrounding granite. Rather like this. So we can trace a pegmatitic sheet in pink here in from the country rock, and it falls apart, blobs out into the main granite body. So lots of detail that we can capture that shows how the granite body has grown by accumulation of magma batches that are partially frozen before each new batch comes in. Of course, the history of incremental intrusion is easiest to track in the country rocks, where cross-cutting relationships are more obvious and give the relative history. But even individual sheets have a story to tell of incremental intrusion of distinct magma batches.
So we've got different generations of granite sheet here. There's this one that goes right across the middle, and that's clearly late. But look at the one that it cuts. It's just above my head here, drops down on the other side, but is folded. So we've got early folded granite veins, perhaps due to the emplacement of the main granite body, cut by these later ones. So a history of sheet granite intrusion. So this granite sheet is actually in itself differentiated, and actually is a composite intrusion. You've got this speckling zone down in here, and this break, which is the edge of this first intrusion, and then there's this later phase on top, and we can tell it's later because these younger crystals are growing off this margin. So it's a sheeted granite sheet. So the contact between granite and country rock isn't simple at all. Really complicated invasion of granite into the Killas.
So these outcrops are really instructive of how granite bodies can grow by incremental intrusion rather than by massive one-off migration of melts into the upper crust. And on a large scale, if you look at the ages of the intrusions across southwest England, you see that granite emplacement and therefore granite melt production spanned over 18 million years. And that makes for a lot of magmatic increments.
So Cornwall isn't just famous for granite, in fact it's more famous for something else, and that's its mining. So let's go and investigate that.
The exploitation of geological resources in Cornwall dates back to the earliest industrial times, 4,000 years ago, the Bronze Age. Bronze is an alloy of copper and tin, and Cornwall provided much of this, exported across Europe. But the old engine stations and chimneys here date from the Industrial Revolution of the late 18th and 19th centuries, servicing underground mines, some of which extend for kilometres out under the sea. Cornish miners are synonymous with deep mine expertise, and their skills were exported by emigration around the world. So quite rightly, this area is a World Heritage Site. Deep mining along the coast here only ended in the 1990s. This is now a museum and a celebration of the skill, determination and sacrifice of the miners. And we can investigate the geology of the metal resources here too, even going underground to find the seams.
Well, these mines are quite low, aren't they?
So this is what ore looks like. A vein of quartz with traces of metal ores. And we can find some of this geology at outcrop. Too small to be economic, of course. The dark minerals here include tourmaline, which doesn't have any value, but also small clusters of cassiterite, that's tin ore. But mineralisation also occurs in a halo of alteration around the vein. We can see the alteration effect on granite, which when unaltered is solid and strong, but when attacked by mineralising fluids looks like this, with cassiterite and other ore minerals forming in the leached out new porosity, eventually creating a mineralised lode like this. This is the prize, seen in a museum specimen. It's over a metre tall. And mineralisation can also occur along arrays of small fractures. And it's this style of composite mineralisation we see in the mine. So does all this mineralisation link to the magmatic history? Is it broadly contemporaneous or much later? Well, for the Land's End area, it's contemporaneous, and also across the province as a whole. The fractionation of magma, residual water plus potential contamination by meteoric water combine as granite melts evolve. The pegmatites are just an earlier part of this evolution. and the mineralised quartz veins are just a little bit more evolved. It's all intimately related, a single complex petrogenetic story. Of course, mining doesn't simply involve digging metal out from the ground. The metal's in ores, and these ores need processing. And at Giva Mining Museum, you can see what was involved, preserved in these old mineral processing sheds. We can leave this industrial heritage for now and get back to the geology. So what's the tectonic setting of the granite and its mineralisation? These are the granites across southwest England, clearly reflected in the gravity anomaly map, which in turn shows that just below the surface, all these granites join up to make a huge mass, the Cornubian batholith. As we've seen, this never operated as a single magma chamber, but is made of many, many distinct pulses of magma injection, evolving in space and time over at least 18 million years. The composition of magma batches themselves changed through time, as we saw at Sennen, and these general types of facies have been mapped out on a large scale. Beth Simons and co-workers at the Camborne School of Mines interpreted trace element patterns to determine the petrogenesis of these granites. During melting and crystallization, different trace elements are partitioned into different minerals, and as the various granites have different mineral compositions, their trace element compositions vary too. So we can test the idea that granites came from partial melting of a metasedimentary source and what the amount of this partial melting was, and how fractionation of these partial melts governs the various granite compositions. So let's examine this plot. It shows whole rock analyses of the abundance of a selection of trace elements normalized against typical upper continental crust. So this plots a 1. So these are the measured values for the Gram-Scatho-like metasediments, and these are the various granite compositions. The plot shows why there's such economic interest in southwest England again. Lithium, for example, is greatly enriched in these granites, and so are other strategically important trace metals. And we can model the differences in granite compositions as products of fractional crystallization, for example, looking at variations in these elements plotted relative to titanium. This shows perhaps most clearly that the G4 and G5 tourmaline and topaz granites crystallized from more fractionated melts. We can also use these analyses to see similarities with the inferred source of the granites as partial melt of the Gram-Scatho-like metasediment. So on these plots, here is the source. And we can model whether the composition of the biotite granites, such as those we find at Land's End, as partial melts of this source rock. So this is our target. So for partial melting of between 10 and 40% of the source metasediment, we can produce the biotite granites. Deviations away from these predicted trends can suggest perhaps that there's been a minor component of melt derived from the upper mantle. But it's worth emphasizing that these different degrees of partial melting and fractionation, and mineralization of course, have happened over a long period of time. So small batches of the crust have melted over this time period, gradually building the Cornubian batholith. And creating its mineral resources. Pretty complex. So all the granite and the region's mineral riches come from melting metasediments, rather like those that form the country rocks to the granites we've seen. But isn't these country rocks? They've not melted here. This is just where the granite melt migrated to, the upper crust. No, the melting metasediments were much deeper down. So how did these metasediments get there? Why did they melt? Well, that's about tectonics. So let's step back. Here are the granites emplaced into rocks that filled various sedimentary basins which formed during the Devonian. The Variscan orogeny restacked these basins, here shown as rather simple inversion structures. So in this interpretation, the region is underlain by continental crust, the basement to these basins. Collectively, the Cornubian batholith emplaced in the upper crust, at the end of the orogenesis, they're post-orogenic granites. But it must have originated from partial melting of the deeper crust. But the catch with this model is that it's not Gram-Scatho-like metasediments that are melting, so this doesn't fit with the geochemistry. As an alternative, this model has the sedimentary rocks deposited not on continental but oceanic crust, then stacked up and thickened by major thrusting. So this has metasediments all the way down. And it's these that are the source of the granites, satisfying the geochemistry. Okay, let's step even further out now and put this into the broader context of the Variscan orogeny. This is a paleogeography at the end of orogenesis. We're here. So let's consider this area. So southwest England is part of the old continental block called Avalonia, and it lies on the northern edge of the orogeny, juxtaposed against the other continental block of the Armorican Massif. Let's think about how these two continental blocks came together as the intervening so-called Rheic Ocean closed up. Avalonia is shown under thrusting Armorica, so Avalonian crust is on top, now eroded if it ever overran the rocks of southwest England. So both this interpretation and the inversion model we discussed and dismissed earlier have southwest England being underlain by Avalonian lithosphere, plus or minus its older crustal roots. So now for another component in our story, another piece in our tectonic jigsaw puzzle. Granites like these around Land's End aren't the only igneous rocks that are post-orogenic in southwest England. The area is punched through by lots of lamprifiers, dikes derived from small partial melting of the upper mantle. So the chemistry of the lamprifiers will tell us about the nature of the upper mantle. So what's the story? The strontium isotope compositions of the lamprifiers are interesting because they define two provinces, one in the north and one in the south. High 87-86 strontium ratios suggest older mantle lithosphere as a source. And we can tie this to the neodymium results and cross-plot these analyses. And the striking thing is that the southern group of samples yield the same composition as lamprifiers in Armorica. But we just said that the lithospheric underpinnings of all of southwest England was Avalonian. Well, this doesn't look like it's the case. These results, published by Dijkstra and Hatch, led them to suggest a major tectonic boundary beneath southwest England that juxtaposes different upper mantle, originally different plates. And it's the southern area that yields the greatest concentration of economic minerals, especially the tin and tungsten. So this is their deep cross-section, with the suggestion of a deep-seated northward dipping subduction that triggered melting for the lamprifiers and maybe even the granites too. So the traditional view of simple northward directed thrusting doesn't fit the magmatic history, Perhaps we need to re-evaluate the risk and tectonics in southwest England to involve substantial strike-slip tectonics, moving pieces of distinct lithosphere in from the sides. And it's this style of tectonics that's recorded in Armorica and indeed beyond. So there's much more to be understood about the risk and tectonic evolution of southwest England, the context for its mineral wealth. And this is not just of historical interest. Really, the knowledge of its economic potential is very underdeveloped. New projects such as this one at United Downs are developed out of old mines and their immediate surroundings, targeting metals that were largely ignored back in the day, but which will play a critical role in resourcing our electrified future. And although many of the existing traditional metal resources are worked out, these were found using really just the surface outcrops and some rather minimal basic geological principles. There's far more exploration that could be done away from these old areas, particularly thinking about deeper structure. In developing new Earth resources, we can bring in new ideas for exploration, but we can also learn from history, not just the geology, but also mineral processing. These are old arsenic works, where the metal was condensed on the walls of chambers like this to be scraped off by hand by workers at huge toxic risk to themselves, and leaving a legacy of contaminated land. Similar things happen with other metals here, including these old tin processing areas.
Even though we're going into the energy transition, we'll still need Earth resources, and even more than before. And as ever, it's a case of balancing the development of those resources against their environmental impact. Strong regulatory frameworks stop messes like this in the future.
And so the next part of Cornwall's industrial history will be much cleaner, with much lower environmental impacts. Southwest England then yields important stories, from granite generation and emplacement, regional tectonics, the generation of metalliferous earth resources, along with the societal issues in their development. I'll certainly be coming back again soon.